Usually, when we try to express a functional relationship between a variable and the other, we make use of a very popular function, y is a function of x. We use this function in mathematics to express a functional relationship that exists between the dependent variable y and the independent variable x. This can actually mean a lot of things when we talk about y and x. But in this case, I want to look at the slope of a line. The slope of a line, or the movement along the y-axis, is a function of the movement along the x-axis. We also use this function to derive the changes that exists in the x and the y variables. These changes are expressed rationally as delta y all over delta x. This is read as change in y is due to a change in x. Now, when we limit this particular expression using something as limiting delta x as it approaches 0 with this function delta y all over delta x, usually we write it in a formal way as dy dx, just as you see it right now. This is what we call the differential coefficient, or the derivative of y with respect to x. Some other popular ways of writing dy dx are y prime, or written as, or called as y dash, fx with f having a prime, that is f prime of x, and many other methods that you may see them in various textbooks. Now, I want to prove at this moment the basic derivative function, or what you know as the differentiation itself. Mathematically, with the function we've generated so far from here and from here, using this one as equation 1, we can say that from this equation 1, where we have y as a function of x, from here we can also prove that if we add the change in y, it can also be seen as a function of x and the change in x, since y is a direct function of x. This will mean that change in y is a function of x plus a change in x minus y. With what we have here, remember that we have initially started this equation by using y as a function of x. So if I substitute fx in place of y, we can rewrite delta y as a function of x plus delta x minus a function of x. Dividing this whole equation using delta x, we arrive at a situation you see right here. Now, since we've also come back to our equation 2 again, remember I mentioned that the limiting factor here is exactly what we call the differential coefficient. So, taking the limit from this level where the change in x tends to 0 will be the same thing as taking the limit of the right hand side where delta x also tends to 0, with f of x plus delta x, close the bracket, minus f of x all divided by delta x, or change in x. What you see right here is what we refer to as the differential coefficient, or what you may call the derivative of a function. I will encourage you to see my other videos that will show you how to apply this first principle of differentiation, and from this we are going to generate the rules that will help us to solve differentiation problems. I hope this proof is simple enough, and I hope you enjoyed it. Thanks for watching, and see you later.